Hello students, this is Dr. Ben, and I'd like to work out this problem from Chapter 4. It's problem number 15 that was on the hand-graded homework that we had for this part of the course. So we have an object, a block, that has a mass of 6 kilograms. And it starts from rest, and it slides down this frictionless inclined plane, and we're given the length of the plane. And we're told that when this block arrives at the bottom, that it has a certain speed, v sub f, and we're asked to find the position, or really the distance from the top of the incline, where the speed of the block is equal to 1/2 of what it is at the bottom. So even though this is a one-part problem, the object is just sliding down the plane with a constant acceleration, we have to consider two different cases. And in the first case, we want to go from the initial point that I have on a pictorial representation to the final point, and in the second case we want to go from the initial point to the point that I have labeled point number 1. Alright, so we have the 3 points indicated on our pictorial representation, and I've already labeled the kinematic variables for those points. So let's go ahead and make our table of what we know and what we want to find. So let's start at point I, and we'll let that be the origin of the coordinate system. So x is going to be equal to 0, t sub I is going to be equal to 0, and v sub I is going to be equal to 0. And at point number 1, which is the intermediate point, the velocity of point number 1 is equal to 1/2 of v sub f. That's what we were given. And then point F, we're told that the final position is equal to 2 meters, and the symbol for the final speed is equal to v sub f, although we don't know what that number is. And we're asked to find the value of x1. So that's going to be the location of the block measured from the top, which is where we define the 0 of our coordinate system. Alright, so in this problem we know nothing about time, so it makes sense to try to use one of the kinematic equations that doesn't have time in it in order to solve the problem. And so that's the third equation on the list that looks like v final squared equals v initial squared plus 2a sub x delta x. So we're going to apply that kinematic equation for our two different cases, and we realize that the acceleration in the x direction is a constant for both of the cases. There's nothing to make it change. Right, so I'll move the paper up a little bit, and we can write down that kinematic equation for both of the situations. So for the first case, where we go from the initial point to the final point, we will have that v final squared equals v initial squared plus 2a sub x times x final minus x initial. And several of those variables are equal to 0, so the object starts from rest, and it starts from rest at the origin. So therefore we have v final squared equals 2a sub x times x final. And I'll put a box around that. Move my paper up a little bit more, and we'll do the same thing from the initial point to the final point. So that will tell us that v1 squared equals v initial squared plus 2a sub x times v1 x1 minus x initial. And again, several of those quantities are equal to 0, so the initial velocity and the initial position are both 0. So that gives us v1 squared equals 2ax times x1. And I'll put that in a box. All right, so the two cases have the same kind of motion, and the acceleration in the x direction is a constant. And even though we don't know what that value is, we can use that fact to eliminate the acceleration algebraically and then solve for the relationship that we're looking for. So I'm going to take both equations in the green box and solve them for the acceleration. So for the first case, I'm going to get vf squared over 2 times xf equals a sub x. And for the second case, I'll have v1 squared over 2x1 equals a sub x. So since the right-hand sides are the same, that implies that the left-hand sides have to also be the same for both of these equations to be equal to a sub x. So we can go ahead and equate the left-hand sides, and I'll change color. So that gives me v final squared over 2xf equals v1 squared over 2x1. And since we want to find the value of x1, I'll cross multiply and get 2x1 over 2xf equals v1 squared over v final squared. Alright, so we're almost there. On the right hand side, the 2's cancel out. So I have x1 over xf equals, and on the right hand side I have v1 over v final quantity squared, which we know is equal to 1/2. v1 over vf is given to be 1/2, and so just one more step will give us that x1 equals xf times 1/2 squared. So this is 2.0 meters divided by 4, which is equal to 0.5 meters. So the block is 1/2 of a meter from the top when the velocity is equal to 1/2 of what it is at the bottom. So there we have it, the solution to Chapter 4, Problem 15.